You are listening to EE Times On Air, and this is EE Times Current. I'm Eric Singer. Today's podcast is sponsored by Synopsys. Our technology, your innovation. Today's guest is Priyank Shukla, Principal Product Manager for the Synopsys HPC IP portfolio, to talk about how 1.6 terabit Ethernet will alleviate the data bottleneck for the world's fastest data center chips in this era of AI. Priyank, let's start with the big news. Back in February, Synopsys unveiled a 1.6 terabit solution. That's a pretty huge milestone in the chip industry. That's going to help us alleviate the bottlenecks in data traffic as that traffic increases from AI workloads. Can you start by giving us a bit of a primer on current standards and really the last 50 years of Ethernet technology to set the stage for how we got here?
Thank you so much, Eric. So maybe I'll back up a bit and I'll start with networking technologies. To set the base at a common reference point, Open System Interconnect, or OSI, came up with a reference model, and they defined different layers for communication for a network. So there are 7 layers that OSI has defined, which starts from application, presentation, session, transport, network, data link, and physical. So the last 2 layers I mentioned, data link layer and physical layer, layer 1 and layer 2, collectively are defined by IEEE through a working group 802.3, and that standard is called Ethernet. And on top of that, layer 3, which is the networking layer, if that's implemented using Internet Protocol Suite, which includes TCP/IP, that becomes the Internet. So when we say there is this Internet of computers, we mean that at level 3, TCP/IP is used, and level 1, level 2 could be different versions, but generally it is Ethernet. And we are talking about different generations of Ethernet. Ethernet started about 50 years back, 1973. And the main aim of Ethernet was to connect multiple computers in a local area network. But as the applications evolved, fast forward 50 years now, we have Ethernet running over different media, not only physical wires, but also across radio frequency, using your phones, using the Wi-Fi router, and so many other technology. So Ethernet is pervasive today. You find this implemented in your handheld device, in your laptops, even your smart TV, and all the way to the data centers. Let's take example of an Amazon shopping page. There you see your product, the product you want to buy, but you see a lot of recommendation. Then you see an option to take this product to your shopping cart, and then you see an option to one-click pay. All these microservices or the section of web pages are executed or rendered by different servers, which would be in different racks in that data center. And there is a lot of traffic within data center to service one of your query. And that traffic today runs over a network which consists of Ethernet. And if that network can be faster, a lot of servers which are connected together, number 1, can respond to your query faster. Number 2, can work together and solve a very complicated problem, doing machine learning to provide artificial intelligence responses.
Obviously, that introduction of 1.6 terabit speeds is a game changer, but some of our listeners may wonder why it's needed now and who exactly stands to benefit from it. Can you shed a little light on that and what its potential impact would be on the industry?
So in computing, hyperscaler's ability of an architecture to scale appropriately as demand is increased for the system. And as we have been talking here, the demand of compute is with more unstructured data. So today, this hyperscaler data centers already have some deployment to do this machine learning and then render all this information to the user. So at this time, as we talk, there are multiple technologies of Ethernet which are in deployment. So there are different clusters that takes different speed. So this AI training cluster or a different kind of machine learning cluster is generally referred as high performance compute or HPC cluster. So in those clusters today, the state of the art is 200 gig or 400 gig Ethernet. So here you will find an accelerator which will have a 400 gig port, and that 400 gig Ethernet port will use maybe 4 lanes of physical layer. In that way, that 400 gig Ethernet packet will be divided into 400 gig SerDes, and then that will go to another accelerator through the network interface card or an optical module or a switch. So these are all the components that use this high speed Ethernet today in an high performance compute AI cluster. You will find some hyperscalers today starting to deploy 800 gig designs. So when I say again 800 gig design, so they will have an accelerator that supports 800 gig, and that 800 gig port will go through an optical module and the whole Ethernet link. So these are very early days for 1.6 terabit Ethernet. So IEEE has 802.3 DJ task force, which is currently drafting the specification for 1.6 terabit Ethernet. So when I say specification, the standards for both layer 1, which is physical layer, and layer 2, which is data link layer. And the challenge here is, as I described, that Ethernet packet goes from one processor to another processor through multiple channels. So the journey of packet starts from one accelerator and then goes through a physical channel. So accelerator will be in the form of a chip. That chip would connect to a rack unit server, which essentially is a printed circuit board. So from chip, you get an Ethernet packet, which has to physically go through that PCB and through connector, through an optical module or a direct attached copper. So from the rack unit, you have a pluggable module that takes this Ethernet frame to different rack unit or a different server. Based on the distance between two racks, hyperscalers use copper cable. So today with 100 gig SerDes and 400 gig Ethernet, it's common to see 2 to 3 meter of direct attached copper. So within a rack, you have 400 gig Ethernet running over direct attached copper. But if this packet has to go to another accelerator of server, which is 10 meters away, so there is no alternative than to go to an optical interface. So in that case, your optical module will be a 400 gig optical module, which will take electrical on one side and will have optical fiber running those Ethernet packets in an optical medium. On the other side, you again have optical module, and that's how the link will get completed. But to make this whole ecosystem, you need all this SoC system on chip to support this new data rate. IEEE, as I was mentioning today, is defining 1.6 terabit Ethernet. And you would have noticed last month we announced that we have the complete solution for Ethernet, meaning data link layer, which consists of MAC, media access control, and the PCS, physical coding layer. These two digital logic and the physical layer, which supports 224 gigabit per second per lane. So in this implementation, you can have 8 lanes of this 224 gig SerDes combined together to provide you 1.6 terabit Ethernet. So with having this fat packet transfer capability, multiple accelerators can connect with each other in a low latency network and provide a better throughput to provide a higher machine learning throughput.
So it's pretty remarkable that you've managed to roll this out even before the industry standards have been set. Can you give us a little bit of the inside scoop on how Synopsys managed this and developed it? And if you can, touch on how it impacts interoperability, which obviously is critical when we're talking about Ethernet and all its applications.
So let me start with an example of the present generation of Ethernet standard 1.6 terabit Ethernet. So there are two aspects to it. One is the layer 2, which is the digital aspect that defines the way the packets are formed, the type of forward error correction technologies the link needs. And then there is layer 1, which is the physical layer that is commonly referred as SerDes or serializer deserializer. So at Synopsys, we have been designing SerDes for last 20 years. It's very hard to believe, but the latest PAM4 technology, which is Pulse Amplitude Modulation Level 4, this technology, which is used for 50 gig today, 50 gig per lane Ethernet today, was first tried for 5 Gbps data transfer way back in 2004. And in that time at Synopsys, we had that solution. So our experience in designing this SerDes technology, both NRZ and PAM4, goes back a long time. So from this experience, we have ideas of about the channels. And the interesting thing here is whenever a new technology comes up at the data center, the channels are not expected to change. That's a good part of this hyperscale data centers. The fundamental unit of this data center is a standard rack, and there are multiple rack units which are standardized today. It's 19 inches standard pizza box kind of structure. So the printed circuit board that goes inside the rack unit and the distance between two chips across generation follows a sort of pattern. So because we have been working in this field for last 20 years, have an idea how technology moves across generation. The printed circuit boards of next generations invariably gets better, so their loss profile changes. And we work with all these ecosystem vendors, PCB manufacturers, connectors, the direct attached copper cable manufacturer, module manufacturer. So as the data rate progresses, we get an idea how the channel is going to be looking 2 years down the line. We know when the ecosystem needs next generation of data rate, and we know where the ecosystem is going. We understand the complete channel for this Ethernet. So we work with all these ecosystem vendors and align our design roadmap with them so that at every stage of our PHY or the SerDes design, we have latest model for all these parameters in this channel. So we somehow try to estimate where the standard would land when that's ratified, and we get some margin, of course, so that when the customer take this design and when anybody incorporates this design and the design goes for production, they would have some margin for operation. With that, we start our PHY design generally 2.5 or 3 years before the standard is expected to be ratified. So here with 1.6 terabit Ethernet, the PHY per lane is going to be 224 gig SerDes. And we have been demonstrating this SerDes from 2022 October. So it's about more than 2.5 years that we have been demonstrating this as a different industry ecosystem platform. And to demonstrate in October 22, we had to tape this one out by end of 21. So we have been designing this 224 gig SerDes for last 3 years. And this is a very mature and robust solution. And we have interoperated this solution, the PHY solution, with different channels, different connector, different cables, and that's that methodology. And then second piece is the logic layer, which is the forward error correction. And there has been a lot of discussion in standard bodies on what kind of forward error correction technologies will be useful and will be sufficient with 1.6 terabit Ethernet. So the way we provide proof point for efficacy of a FEC is our test chips include various form of this FEC. So Reed-Solomon FEC is something which is most commonly used in this Ethernet standard. And FEC or forward error correction is just a digital error correction technology where you pre-stuff a packet with some bits so that when you receive and those pre-stuffed bits show some error, you know the packet was faulty. So that way you retransmit the packet and your total throughput, total bit error rate goes down. So you have pre-FEC bit error rate, which defined by standard, and then FEC improves the bit error rate. So that's the rule of the FEC. And there are a few FECs that industry is working. Reed-Solomon 514, 544 is one that we have included in our test chip so that we can demonstrate performance. And then with 1.6 terabit, there was some discussion about the soft FEC and also different ways of FEC, the way FECs are implemented with multiple lanes interleaved. So we do all the silicon proof point so that whenever the standard comes up, the implementers or the whole ecosystem gets an idea of the performance of the link. And that's what we have been doing with 56 gig and 112 gig SerDes, and 224 gig SerDes and 1.6 terabit is no exception.
Achieving speeds that fast seems like a pretty monumental task given the complexity of the technology involved. Can you walk us through some of the fundamental components of the solution and perhaps explain why it is such a significant challenge in the current landscape?
So the fundamental components of the solution is a PHY and a controller, which consists of MAC and PCS, working together in a low latency fashion. It's about the complete solution, PHY and controller, not just a standalone PHY and a standalone controller. The reason for this is there are a lot of implementation with 1.6 terabit Ethernet where FEC is distributed between PHY and the controller. And this offers an opportunity for a solution provider to provide a differentiated solution. So while designing this PHY and controller solution, we optimize the data path and reduce the number of pipeline stages between PHY and controller. Every pipeline stage in the data path adds to latency. And this 1.6 terabit Ethernet solution from day one are expected to go and empower machine learning solution. And their latency is most crucial because more latency degrades the throughput of the training algorithm. So we had that in mind when we were designing the solution, and we made sure our Mac PCS team sits together with the PHY team, and together we were able to reduce latency by about 40 to 50%. And the second part was the way this controller is implemented. And we provide some area reduction technologies there, the way this RTL is register transfer level description of the logic is implemented in the SoC. And we offer up to 50% area saving compared to the previous generation, which is 400 gig or 800 gig solution. And from PHY point of view, the two most important metric are power and latency. And with this solution, we have saved 50% of power consumption of this architecture compared to 112 gig. And with respect to latency, this is 40% lower latency. So this solution, PHY and controller together, will ensure 50% power reduction and 40% latency, which will be able to provide infrastructure to train next generation of large language models.
All right, let's get down to brass tacks and talk a little about the physical layer, or PHY. It's often rife with its own set of challenges. We hear about analog complexities, PAM4 versus NRZ, maintaining signal integrity as we get into speeds like 224 gigabit. Can you delve into some of the specific obstacles you're currently grappling with in that area?
So 50 gigabit per second per lane was the first time when the Ethernet ecosystem was dealing with NRZ, non-return to zero modulation, to PAM4 modulation. And this happened around 2018 to 2020. And we were enabling the ecosystem at that time, working with different customers, different application spaces, such as switch, optical module, accelerators, and processors. We were able to see the challenges during deployment phase of those 50 gig PAM4 designs. And since then, we have taken that feedback and rolled into those learnings into our next generation 112 gig SerDes. So our PAM4 PHYs have a very robust adaptation and calibration algorithm. So this PAM4 PHY, pulse amplitude modulation 4-level PHY, are typically implemented using a receiver which is implemented as an ADC, analog to digital converter, and DSP, digital signal processing receiver signal chain. So here, there is a lot of algorithms that can be implemented to calibrate and optimize and performance of this receiver. So we had all these learnings from 50 gig and 100 gig SerDes deployment on field. So we know if you have multiple lanes in a SoC, how power supply rejection ratio degradation affects performance of the PHY. So our calibration algorithm accounts for those variations. So all the field learnings we have had for last 4 years have been rolled into this 224 gig SerDes design in form of the firmware that we provide. So there are a lot of power supply coupling issues that we have seen and helped our customers to eliminate with the robust adaptation algorithm we have. And second most interesting part of deployment of the SerDes is with respect to data center operation. So as soon as the SerDes or the chip start operating, the temperature of the chip goes up because these are high-speed SerDes which are in a system on chip that operates at, let's say, 1 gigahertz to 5 gigahertz of clock frequency. So the whole chip takes a lot of power, and that power gets dissipated into heat, which means the temperature will go up. And when the temperature goes up, the SerDes needs to perform the same way, the way they were performing when the temperature was lower. So this becomes crucial performance aspect of the SerDes during the deployment phase. So this is something what we call temperature cycling or temperature drift. And because we have seen this kind of deployments for last 4 or 5 years in the data centers, we have designed and characterized all these IPs on the SerDes to ensure that they can start at any temperature, minus 40 or 20, and while they're operating, the temperature can go up to 125 degrees C, but the PHY performance doesn't degrade. So all this is incorporated as form of the calibration and adaptation algorithm I was referring to. And that became so effective because this is ADC DSP based architecture and because this is PAM4. So PAM4 threw some challenges, but with this firmware and the DSP techniques, we were able to overcome. And this multi-generation learning has helped us to help our customers with the 224 gig deployment with very little unknown surprises to the customers.
I'd like to dig in a little bit more to the standards that we mentioned earlier. There's quite a lot of chatter currently about the Ultra Ethernet Consortium and its role in hyperscale data center space. Can you clarify how the Ultra Ethernet Consortium differentiates from the IEEE and what objectives they're aiming for in this evolving market?
So Ultra Ethernet Consortium that started their standardization activity last year is trying to define Ethernet as a fabric that can be deployed for cache coherent, low latency, compute disaggregation architecture. So I said a lot of jargon here. So cache coherency means the memory that a processor is accessing is shared with another processor which is working on the same problem instantly. So if this happens, let's say processor A and processor B have the same set of memory, they can work on a problem more effectively. And to do this, you need a cache coherent network. That's what cache coherency is called. So if you can do this cache coherency across racks or across servers, you can split a problem across multiple servers and you can solve a bigger problem. That's essentially what powers next generation of machine learning. So as we were talking large language models, so ChatGPT 3 had 175 billion parameters and ChatGPT 4 is expected to have more than 1 trillion parameters. So all these parameters need to be processed in multiple processors which are actually physically separated, and those processors need to be connected cache coherently. Those could be processor and accelerator. So the fabric that connects them today is Ethernet, but there are a few challenges that Ethernet faces here. Ethernet, by definition, is a best effort protocol. By best effort protocol, what I mean, there is no retry buffers in this protocol layer 1 or layer 2. So Ethernet tries to just send the packet over channel and expects the receiver will get the packet. And if there's a packet loss, after a long time when receiver times out, the whole packet will be sent. So the problem with this approach is this feedback loop is longer. So if there is a packet loss, it takes a long time to correct that error. And just imagine a case where you are splitting a process between these two processors, and one error was corrected after a long time, let's say 100 millisecond. So the whole work these two processors have done for 100 millisecond will go waste. So the throughput of the whole system, the machine learning algorithm, will go down. So in networking topology, this latency is called tail latency. So your typical mission mode latency was not as much, but when there was one error, the latency just shot up to milliseconds order. So the whole system throughput went down. So this problem needs to be corrected. And the challenge here with Ethernet is the data rates are so high that if you have retry buffers in your layer 2 or MAC and PCS, you need a very large amount of SRAM, which will increase the size of chip, which is not practically possible. So there needs to be some layer 3 solutions, which can be done at a switch level or at a host level, not at each link, but at some points in the fabric. And Ultra Ethernet Consortium is taking the lead to define those changes on top of Ethernet so that the tail latency goes down. And also, there are a lot of meaningful diagnostic metric that Ultra Ethernet Consortium is suggesting that will provide some insights into this journey of packets and will able to identify the point of failure, and the throughput of whole fabric can be improved based on the diagnostic we have. So Ethernet just talks about raw bit error rate, and sometimes it talks about frame loss ratio. But Ultra Ethernet Consortium is coming up with new diagnostic capabilities such as mean time between failure, mean times between errors. So those will provide more insights into the link health and how this can be improved. So Ultra Ethernet Consortium will optimize Ethernet for this low latency, low tail latency, cache coherent network, and will allow this machine learning clusters to process next generation models, which could be large language model for more than tera parameters.
Priyank, thank you so much for sharing your expertise with all of us today.
Thank you to the whole team for providing me this opportunity. Really appreciate it. Thank you.
That brings another episode of EE Times Current to its end. Thank you for listening, and thanks again to our guest, Priyank Shukla, Principal Product Manager at Synopsys. EE Times Current is available through the major podcast platforms, but if you get to us at our website at eetimes.com, you'll find a transcript along with direct links to the other stories we've mentioned and other resources. EE Times Current is produced by EE Times. It was engineered by Taylor Marvin at Coop Studios. I'm Eric Singer. Thanks for listening.